Welcome to the deep dive.
It's good to be here.
Today, we are undertaking a very specific mission. We're going to systematically dismantle and understand the structural world of ceramics. Specifically, we're focusing on the most abundant materials on Earth, the silicates and the aluminates. We're literally diving into the foundation, the bedrock of our planet.
That's exactly right. And our source material for this, Chapter 24 of Structure of Materials, it just lays this world out with incredible precision.
Right.
So our goal isn't just to skim the surface, it's to trace the entire structural hierarchy exactly as the text presents it. We're moving from the simplest, the single atomic building block, all the way up.
All the way up through complex three-dimensional frameworks, non-crystalline glass, and even into advanced nanomaterials.
Exactly.
So we're following a scientific roadmap here, making sure every complex formula, every crystalline linkage, it's not just listed, but it's fully unpacked and hopefully visualized for you.
Yeah, if you want to understand why a gemstone is hard, or why clay is soft, or even why glass is transparent,
The answer is in the atoms.
the answer lies in the atomic arrangement we're about to explore.
But before we get structural, we have to define what we're even talking about. What is a mineral, according to this context?
Well, we're using the classical rigorous definition, the one established by experts like Klein and Hurlbut.
Okay.
So, a mineral is a naturally occurring homogeneous solid. That's the first part. It must have a definite chemical composition, though that can sometimes be variable, and this is crucial, a highly ordered atomic arrangement.
And formed by inorganic processes.
And formed by inorganic processes. Yep.
That sounds vast. The source material lists 12 massive classes of minerals. Everything from native metals like copper and silver to oxides like hematite, carbonates like calcite. Why are we focusing so intensely on just the silicates?
Because silicates are, well, they're the kings of the crust. They form the largest portion of the Earth's crust, period. They contain the greatest number of identified species, and their material properties are just remarkable. They're famous for their high hardness, incredible resistance to corrosion, and often their transparency or translucence.
So these are the materials that really survive and define our planet's chemistry.
They absolutely are.
Okay, let's unpack this structural hierarchy. Everything in this entire system, the gemstones, the clay, the sand, it all comes down to a single fundamental unit. What is it?
It is the basic anionic unit of all silicate structures. The silicon-oxygen tetrahedron. You'll see it written as text SiO44.
And how should we picture that?
Conceptually, just picture a pyramid with four corners. In the very center, you have the small, highly charged silicon cation, that's TexSiO+, which has a positive cationic valence state of +4.
And at the corners?
At each of the four corners, you'll find a larger oxygen anion, the texture over. And that tetrahedron, that little pyramid, is the structural currency of this entire chapter.
And this is where we have to talk about the aluminate side of things.
Yeah.
Because silicon doesn't always get to be in the center, does it? Aluminum is often substituted in.
Absolutely. In the world of aluminosilicates, that textile 4+1 is frequently substituted by the slightly larger textile 3+ jacken.
And that substitution is structurally critical.
It immediately changes the game. See, aluminum isn't restricted to just that four-fold tetrahedral coordination like silicon is. Textile 3+ often involves both tetrahedral and octahedral coordination.
Which allows for way more complex ways for the structures to link up and stabilize themselves.
Vastly more complex ways, yes.
So the key to understanding the sheer diversity of silicates, the difference between soft talc and hard quartz, it's not the unit itself. It's what happens between the units.
It's all about the linkage.
It's all about the linkage.
Precisely. The variety is determined entirely by how these textile-4,4 tetrahedra link together by sharing their vertices, the oxygen atoms at the corners. The fewer vertices they share, the simpler and more isolated the structure.
Okay, let's try to visualize this linkage, like in the book's diagrams. If we start at the simplest sort of zero-dimensional end, we just have the isolated tetrahedron. It shares 0 vertices.
Right. Now share just one vertex, and you form a double tetrahedron unit.
Like 2 pyramids touching at a single tip.
Exactly. Then, if you link them linearly, so they each share 2 vertices, the chain just continues indefinitely. That creates what we call an infinite single chain.
And if that chain links back on itself, sharing 2 vertices to form a closed shape.
You get a ring structure. And from there, the structures get wider. You can have parallel chains link up to form a double chain.
By sharing alternate vertices.
Right. And finally, if each tetrahedron shares 3 of its 4 vertices, you move into the two-dimensional realm and create these infinite sheets.
And that subtle difference in how many corners are shared, that determines the resulting stoichiometry.
It determines the charge in the anionic unit, the text SI weight way. And as we're about to see, that dictates everything about the material's properties, whether it's prone to cleavage or if it's incredibly dense.
Which brings us to the formal taxonomy, right? The 6 silicate subclasses laid out in Table 24.2.
Yes, we really need to list these 6 because they form the spine of our entire journey today.
Okay, lay them out for us.
Number 1, orthosilicates, also called nesosilicates. These are the simplest. They feature completely isolated text SiO44 tetrahedra, think olivine and garnet.
Isolated, got it.
Number 2, pyrosilicates, or sorosilicates. They're defined by sharing one vertex, creating that double tetrahedra unit. The textile hemimorphite is the classic example here.
Okay, and number 3.
Number 3 is metasilicates or inosilicates. These are the one-dimensional structures. So that includes both the infinite single chains with the charge of text SAO like the pyroxenes and also the rings or cyclosilicates like beryl.
Right, now for the more complex linkages.
So number 4, double chain metasilicates. These are the amphiboles. As the name suggests, they're infinite double chains. The anion unit is text ACI6. Tremolite is the one to remember there.
And number 5, the 2D structures.
The phyllosilicate. These are the infinite sheets with the formula text O2, text O52, where 3 vertices are shared. This is the family of talc and mica, materials defined by their layered nature.
And finally, the 3D structures.
Number 6, tectosilicates, the 3-dimensional framework structures. Here, all 4 vertices are shared. This leads to compositions like neutral text SiO2, which is quartz, or complex aluminosilicates like feldspars and zeolites.
That is the complete structural map. So let's start the deep dive into specifics, beginning with the simplest category, the orthosilicates.
The orthosilicates.
Their defining feature is that the text SO44 tetrahedra are isolated. They don't share oxygen atoms with each other.
No, instead they're linked together by surrounding dications, which are often housed in octahedral coordination. And our first example is olivine, a material so crucial it makes up a massive percentage of the Earth's mantle.
Wow.
So olivine exists within this quaternary system, text MOO, text SAO, text EV22, but it's most famous for forming a complete solid solution series between 2 major end members.
And those are?
Forsterite, which is magnesium-rich, text SO, text SiO44, and phyllite, which is iron-rich, text IO44. You find olivine in igneous rocks like basalt, and its beautiful green gemstone varieties called peridot.
The August birthstone.
That's the one.
Okay, a complete solid solution series. Let's break that down. That means structurally, the magnesium and the iron can just seamlessly swap places in the lattice at any proportion.
At any proportion between 0 and 100%. Exactly. And to visualize compositions like this, the source introduces a concept we should probably slow down and explain.
The Gibbs triangle.
Yes, the ternary system phase diagram. Imagine an equilateral triangle. Each point, each apex A, B, and C represents 100% of that component. Any point inside the triangle represents a unique composition where all 3 components add up to exactly 100%.
Okay, so how does that actually help us read the composition from a point on the diagram?
Well, if you stand at a point inside the triangle, the concentration of component A, for example, is proportional to the perpendicular distance from your point to the opposite edge, the BC side.
I see.
So if you move along a line that's parallel to that BC edge, you are maintaining a constant concentration of A, even while the ratio of B and C is constantly changing.
It's a pretty remarkable graphical tool. I can see why geologists would use it to map complex compositional changes, like what happens in the olivine system during crystallization.
And the source also provides a pseudo-binary phase diagram, which is like a slice through this bigger system. And that diagram shows us that olivine's melting is what we call congruent.
Oh.
It means when the solid transitions to liquid, it does so at a single temperature without changing its bulk composition, which, it simplifies understanding how these magma compositions evolve as they cool.
Okay, so let's get back to the pure structure of forsterite, the text SiO4. How are those isolated tetrahedra actually arranged?
The oxygen anions, the text O2, form what's called a quasi-hexagonal close-packed anion lattice. So it's a very dense arrangement of the oxygens.
Okay.
And the small text I4 plus capations occupy the tetrahedral sites. The small space is defined by 4 oxygen atoms.
Yeah.
The larger text emications occupy the octahedral sites, which are defined by 6 oxygen atoms.
Now, the source compares this structure to spinel. What's the key structural difference that makes forsterite an orthosilicate? defined by its isolated tetrahedra.
The defining characteristic is just that, isolation. While both forsterite and spinel have these close-packed oxygen structures with cucations in tetrahedral and octahedral sites. In forsterite, the text-SiO4 tetrahedra are strictly isolated. They do not share edges with the surrounding textman plus octahedra. They only share vertices, and they use those to link the chains of octahedra together.
And that isolation of the highly charged silicon is crucial.
It's crucial for promoting density and high stability under pressure, which is exactly why olivine is so prevalent deep within the Earth.
Moving on to another orthosilicate classic, we have garnets, the January birthstone. These also have isolated text-SiO4 units, but the structure is much, much larger.
Garnets are structurally magnificent. They follow the general formula, textoic, textostatal. And to visualize this, you have to understand that the cations occupy three very distinct specialized sites.
Okay, what are they?
The D cation is the small text-Si4 plus 9 dystoria, four-fold coordination. The A cation, often aluminum or iron, is in the octahedral site, six-fold coordination.
And a C cation.
The C cation is often a large ion like calcium or magnesium, and it occupies this unique dodecahedral site.
Dodecahedral, so 12-fold coordination.
12-fold coordination.
Yeah.
And that large size and high coordination is absolutely critical to the stability of the garnet structure.
12-fold coordination. I mean, given the three distinct sites and the complexity, it makes sense that the unit cell would be massive.
It truly is. The garnet structure is cubic, belonging to the space group textol. The unit cell contains 8 full formula units,
which means 160 atoms in total.
160 atoms. It's densely packed and highly symmetric.
How are we supposed to visualize this complexity? The source says you can construct it from smaller blocks.
Yes, that's the trick. The visualization technique divides the cubic unit cell into 8 smaller alternating blocks called octants. So you can conceptualize the entire unit cell as being built from these alternating building blocks.
Like what?
One block might be text M2, text O4, sort of like a distorted olivine building block, and the next block is text M3, text O2. You stack these 2 by 2 by 2 blocks, and they interlock perfectly to form the full, massive cubic unit cell of the garnet.
You mentioned the importance of the large C cation size for that dodecahedral site. Why is ionic size so absolutely crucial for garnet stability?
Because the geometric demands of that dodecahedral site are very specific. If the cation trying to fit into that 12-fold space is even slightly too small, the lattice will just collapse or distort dramatically.
And we can see this in synthetic materials, too.
Oh, powerfully. It's illustrated by the synthesis of technologically important materials like the rare earth garnets, like yttrium iron garnet, or YIG, which is used in electronics. The large ionic radius of yttrium, the TeXuY+, is the non-negotiable requirement for stabilizing that complex, highly symmetric lattice.
Okay, beyond olivine and garnets, what other orthosilicates should we spotlight?
Zircon, text ZrSiO4R4. Definitely important, the December birthstone. Zircon is another great example where the isolated text SiO44 tetrahedra are linked by large polyhedra. In this case, it's zirconium occupying a dodecahedral polyhedron.
Right.
And while it's incredibly dense, the structure is surprisingly easy to break compared to, say, diamond. It shows that symmetry and density don't always guarantee ultimate strength.
And then we get to one of the most elegant concepts in chemistry, polymorphism.
Yeah.
The trio of kaolinite, andalusite, and silicates.
Yes.
All three share the exact same chemical formula, text-SiO5,5, but they're completely different minerals. Structure is the only variable here.
It's the ultimate chemical chameleon. These polymorphs really illustrate how the coordination of the aluminum bation, the text 3+, determines stability under different conditions.
So let's take kaolinite.
Kaolinite is the high-pressure, low-temperature polymorph. Structurally, its aluminum ions are exclusively octahedrali coordinated. They're all text-AO07.
And what does that structure look like?
It's tough. It's built from these chains of edge-linked octahedra running parallel to the C-axis, and these robust chains are cross-linked by the isolated text-AO44 tetrahedra.
So kaolinite is all about those tightly packed, high-pressure octahedra. What changes when we look at siliconite?
Siliconite is the high-temperature, moderate-pressure version, and here the aluminum is found in both four-fold, so tetrahedral, and six-fold octahedral coordination.
A mix.
It's a mix. The structure links edge-linked textile-6-ion to alternating chains of textio-03N4 and tex-AO for tetrahedra. The shift in aluminum coordination is the physical manifestation of the change in pressure and temperature. It just demonstrates that structure controls everything.
That concludes the isolated zero-dimensional structures. We are now transitioning into the one-dimensional linkages, where the tetrahedra finally start touching. We begin with pyrosilicates, or sorosilicates.
Pyrosilicates, also called disilicates, they're defined by having isolated pairs of text-SiO4 sur tetrahedra that share exactly one vertex.
One vertex.
Just one. This results in the characteristic texto-7 structural unit. If you break that one vertex, you get an orthosilicate. If you share two, you start forming a chain. This is the structural middle ground.
And the primary example provided is epidote.
Epidote, that's text 2, text A. It's a sorosilicate known for its deep green color, and it's pretty complex formula.
So if you try to visualize the structure, where do you start?
You'd first see the backbone, and the backbone is made of chains of edge-sharing aluminum-centered octahedra, actually similar to what we saw in kaolinite.
Okay, so aluminum octahedra are forming this long, robust spine. Where do the silicon units fit into that arrangement?
The octahedral chains are linked together by the silicate groups. And what's so fascinating about epidote is that it's a structural hybrid.
A hybrid.
It incorporates both single text SiO4 tetrahedral groups, so it's borrowing from the orthosilicate class, and the signature double text O70 said pyrosilicate groups.
That makes it a great case study. It shows how minerals in nature, they rarely conform to these simple, clean lines. It's using multiple types of linkage at the same time.
Exactly. And because of this open, complex framework created by the mixed linkage, the large calcium cations, which are there to balance the charge, they're forced into these large cavities. And these calcium atoms end up with very high coordination numbers, 9-fold and even 10-fold coordination, just to fill the structural voids.
Moving forward, we reach the classic 1D structures, the metasilicates or inosilicates. These feature infinite chains or rings of tetrahedra.
Right. And the formal stoichiometry of a perfect chain here is TecASO32. We look first at wollastonite, TecSCASO33. It's a mineral often associated with the high-temperature reaction between limestone and silica.
And how does that infinite chain look structurally?
Wollastonite is typically monoclinic. The key characteristic of its chain is that it's not straight. It's described as kinked. It has a repeat of every 3 tetrahedra, linked by sharing 2 vertices along the chain direction.
And what holds the chains together?
These kinked chains are connected laterally by large calcium-oxygen octahedra.
And the source material specifically guides us to view this structure along the 100 crystallographic direction to make the chains visible. It really shows how crystallography is necessary to translate this complex 3D reality into digestible 2D diagrams.
It really does. Next, we look at a pyroxene mineral, jadeite. Text ALC2, text O56. This is the highly prized ornamental gem jade. It also uses these infinite text SiO4 tetrahedral chains. But unlike wollastonite, which uses large calcium polyhedra, jadeite chains are linked through aluminum octahedral coordination polyhedra.
And that gives it a very particular look.
A very particular look. When you view it from the side, the infinite chains and the coordination polyhedra interlock in a way that creates these distinct, massive block-like units. They're often described as an I-beam structure.
An I-beam. So that configuration must be very stable and tough.
Very tough.
Now, what if the chain connects to itself? We move into the cyclosilicates, the rings, and the repeating unit here is beryl.
Beryl, that's text O2, it's structurally defined by the formation of these 6-member rings of tetrahedra, giving it the large anion unit text to weight.
And these rings, they must leave enormous gaps in the crystal structure.
They do, and that is their superpower. These stacked rings create wide, open channels running right through the mineral. And these channels contain 12-fold coordination sites, large enough to capture and house sizable foreign ions.
Like cesium, lithium, sodium.
Even neutral molecules like water. And these impurities, they're often what give the gemstone its color. The deep green of emerald or the pale blue of aquamarine are direct results of trace elements that get trapped inside those silicate rings.
So the structure is literally a chemical trap that changes the gem's appearance.
It is, and these rings are connected laterally by small beryllium-oxygen tetrahedra and aluminum-centered octahedra, which stabilizes the whole large channel structure.
The final step in the 1D world is the double chains of tetrahedra, the amphiboles. This is where the complexity of the chain structure increases, resulting in the text O62 unit.
Right, and our example is tremolite, text OK2-22. It's a crucial member of the amphibole group. Here, the single chains link up laterally to form a much wider, infinite double chain.
How should we visualize this double chain structure?
Well, if you look down the chain direction, the structure is often described as forming a snake or a repeating S shape. These double chains are strongly linked together by magnesium octahedra. The large calcium cations then fill the resulting large voids in the structure. And just like the pyroxenes, this interlocking structure results in what are called staggered I-beams.
Another I-beam.
Another one. It's a highly efficient way to build a tough, elongate, and often fibrous mineral.
So the transition from single chains, the pyroxenes, to double chains, the amphiboles, it fundamentally changes the geometry and the size of the gaps in the structure.
It does. It accommodates different linking ions and results in totally distinct material habits. It just shows the power of a subtle structural change. One extra link fundamentally alters the mineral's appearance and its mechanical properties.
We've moved from isolated points and 1D strands, and now we jump to the two-dimensional world, the phyllosilicates. This is the world of mica and clay.
Yes, the phyllosilicates. They're defined by Textus I544 tetrahedra that share 3 of their 4 vertices. This creates an infinite, perfectly planar layer, which is represented by the anion unit text O.
And the structures here are described using this stacking notation of T-sheets and O-sheets, tetrahedral and octahedral.
Right. The T-sheet is composed of those linked tetrahedra with the apical oxygens, the tips of the pyramids, all pointing toward the O-sheet.
Okay.
The octahedral sheet, the O sheet, is a layer where kaolinite, typically aluminum or magnesium, fill the interstices, and we can classify them based on how they stack. It's either TO, which is a 1-to-1 structure, or TOT, a 2-to-1 structure.
Let's start with the mica group, which uses that 2-to-1 TOT stacking structure. Muscovite is the classic example.
Mica structures are the ultimate illustration of structural consequence. The individual TOT sheets are chemically robust, they're very strongly bonded.
Right.
However, these massive double sheets are separated by an interlayer cation. In muscovite, this is the potassium ion, the textile, residing in a high 12-fold coordination site.
And here's the secret to mica's properties. The layers are strong, but the glue between them is weak.
Precisely. The weak electrostatic bonding provided by those potassium ions between the robust TOT stacks allows for incredibly easy cleavage.
Meaning you can peel it.
You can peel it into incredibly thin, flexible sheets with very little effort. It is a stunning example of how a material can be simultaneously part of the Earth's foundation and easily separable by hand.
The source also distinguishes based on how fully that octahedral layer is occupied.
Yes, the concentration of the M cations, like magnesium or iron, filling the octahedral sheet determines the classification. If the layer is fully occupied, we call it trioctahedral mica.
And if not?
If only 2/3 of the sites are occupied, like in muscovite, it is dioctahedral. This slight difference in occupancy changes the structural geometry and the type of stability required.
Now for the 1-to-1 TO structure. Kaolinite, the most important clay mineral.
Kaolinite is a 1-to-1 structure where the tetrahedral sheet sits directly above a sheet of edge-sharing aluminum octahedra, and this entire double sheet is stacked infinitely. The critical structural element here is what holds the adjacent double sheets together.
And that element is hydrogen bonding.
This is the key to understanding why clay is clay. The weak bonding between the stacked TO double sheets is maintained by hydrogen bonds. These form between the OH groups on the top of the octahedral layer and the oxygen anions on the bottom of the adjacent sheet.
And that weak directional bonding is everything.
It allows the sheets to slide easily past one another when they're wet or under stress. It makes the minerals soft, plastic, and highly cleavable.
So if mica's weakness is a single large concation separating strong layers, kaolinite's softness is due to hydrogen bonding, the weakest common bond linking its layers.
Exactly.
We have arrived at the final linkage, the three-dimensional structures, or tectosilicates. Here, all 4 vertices of every single tetrahedron are shared with other tetrahedra.
This maximal linkage results in the highest possible density of connections. And if we assume no cation substitution, the resulting compound is charge neutral. Text other 2-1. Quartz is the prototypical example. But the moment we introduce aluminum, the charge game begins.
Right.
When an aluminum, text 3+, replaces the higher charge silicon, text A4+ loader, the network develops a negative charge. It's often represented by the anion per bell and LO2.
So to maintain charge neutrality in the overall crystal,
You have to incorporate additional large cations, sodium, calcium, potassium. They get incorporated into the vacant spaces within that 3D network. And this is the mechanism that creates the vast families of minerals like feldspars and, very importantly, zeolites.
let's start with quartz.
Quartz, text SiO2, is the prototech for this class, maximal linkage. It exists in many polymorphs, stable across huge ranges of temperature and pressure, like alpha and beta quartz.
And the text uses quartz to illustrate Linus Pauling's empirical rules for stable crystal structures. This is a foundational concept.
It is a critical technical segment we need to walk through. So let's look at Pauling's rules. Rule 1 deals with the coordination polyhedron and the radius ratio.
Okay, the radius ratio.
The rule dictates stability based on the radius ratio Cation radius over anion radius. For silicon and oxygen coordination, the theoretical ideal critical radius ratio for perfect tetrahedral coordination is 0.225.
But the calculated ratio is a little different.
It's slightly smaller, 0.167.
So the silicon atom is a bit smaller than ideal for that perfect fit. What's the structural implication of that mismatch?
It implies that the structure isn't perfectly symmetric. It allows for slight geometric distortion in the tetrahedra, which is key to understanding the various polymorphs of text SiO2. But the structure remains stable.
Because of Rule 2.
Because we move on to Rule 2, the electrostatic valency principle. This states that the sum of the electrostatic bond strengths arriving at an anion must equal the magnitude of the anion's charge.
So how does that work for quartz?
In text SiO2, the silicon bond strength is +4 divided by 4, which is +1. Since every oxygen anion is shared by 2 silicon atoms, the sum of bond strengths reaching that oxygen is 1 + 1, which equals 2.
And the oxygen charge is -2.
So the structure is perfectly electrostatically balanced, and that explains quartz's remarkable stability.
And Rules 3 and 4, they just reinforce this concept of shared geometry.
Yes. They emphasize that sharing vertices rather than edges or faces is highly preferred, especially for cations with a high charge like silicon. It maximizes the distance between the highly charged nuclei, minimizing electrical repulsion. Quartz does this perfectly.
Now, the 3D framework is not always dense like quartz. Sometimes it contains massive functional cavities. We look first at sodalite.
Sodalite, texochil. It's a feldspathoid mineral with a 1-to-1 silicon to aluminum ratio. Its structure is defined by the sodalite cage.
And we have to visualize this pretty complicated geometry.
We do. The silicon and aluminum tetrahedra link up in a pattern of 24 tetrahedra to form a complex polyhedral unit, a truncated octahedron.
Which is basically a highly symmetric 14-sided figure where the corners are sliced off.
Correct. And the key is that these cages are large internal voids. The sodium and chloride ions fill these voids. However, in sodalite, these cages are isolated. They are large, but they don't connect to form continuous channels. And this lack of interconnectedness is what distinguishes sodalite from our next example, zeolites.
Zeolites, perhaps the most commercially relevant crystalline silicates we'll discuss today, specifically because they are framework silicates with interconnected channels.
This connectivity changes everything. Zeolites are defined by interconnected text-AO4 and text-AO4 tetrahedra that form large, vacant channels running throughout the entire crystal structure.
What are the applications that make this structure so vital?
Primarily ion exchange, molecular sieving, and catalysis. For ion exchange, they're famously used in water softening.
How does that work?
When hard water flows through the zeolite, the framework captures the undesirable calcium and magnesium hardness ions, and it exchanges them for loosely held, charge-balancing sodium ions.
In the molecular sieve function.
That relies on the precise, uniform size of the channels. Only molecules smaller than the channel opening can pass through. This size selectivity makes zeolites indispensable in the chemical industry for separating mixtures and, critically, for industrial catalysis.
Where you need that shape selectivity.
Exactly. You only want reactants of a specific shape or size to enter the active site within the channel.
The text mentions chivazite as a practical example.
Shapeazite is a common natural zeolite, used commercially not just for simple filtration, but for far more sensitive applications, like removing harmful cesium and strontium radioactive isotopes from nuclear effluents.
Wow.
Its structure, with its clear interconnected channels leading to large voids, perfectly facilitates that capture mechanism.
Finally, in this complex structural section, we have the highly specialized fullerenoids.
These are fascinating. First synthesized in 2004, these materials are based on highly complex 3D networks of aluminum tetrahedra. They get their name because their structure involves the formation of pseudospheres, specifically textile units,
which geometrically resemble the famous C60 fullerene molecule.
Exactly, though here they are part of a continuous macroscopic crystal framework.
We've concluded our discussion of ordered crystalline silicates. So now we move into the realm of the disordered. The non-crystalline and nanomaterials. And we start with the most common amorphous silicate glass.
Amorphous silica, or TeX-SiO22, is globally important, and the structure of glass is explained conceptually by Zachariason's continuous random network model, the CRN model, from back in 1932.
What does the CRN model say about the structure of glass?
The key idea is local order, but no long-range order. The preferred local tetrahedral coordination of silicon surrounded by 4 oxygen atoms is perfectly maintained. The tetrahedra still share vertices, just like in quartz, but the structure lacks long-range translational periodicity. There's no repeating unit cell. And this randomness allows the crucial silicon-oxygen-silicon bond angles to vary widely, resulting in an amorphous material that lacks a sharp melting point.
And Zachariason created a set of 4 empirical rules to predict which compounds would be good glass formers.
Yes, and these rules are all based on geometry and charge balance. 1. Ions must be surrounded by oxygen polyhedra. 2. Oxygen must act as a bridge and be twofold coordinated. 3. The cation coordination number has to be small, like 3 or 4.
And number 4 is the most critical.
It is. The polyhedra must share only vertices, not edges or faces. Sharing only vertices allows for the maximum amount of angular flexibility needed to form a random network without it collapsing.
So pure text SiO2 is a perfect network former. But most commercial glass is impure. We add what are called network modifiers. What are they and what do they do?
Network modifiers are typically alkali or alkaline earth oxides like text or textrapero. When you add them, they do exactly what their name implies. They break the continuous silicon-oxygen network.
How?
They can't be incorporated into the lattice, so they wedge themselves into the structure, creating dangling bonds, what we call non-bridging oxygen atoms.
And the structural consequence of breaking the network is what?
It drastically lowers the melting temperature, which is essential for glass working and blowing. You don't want to work glass at the temperature required for pure quartz.
But there's a trade-off.
There is. This ease of manufacturing comes at a cost. By breaking the network, you decrease the material's chemical durability and its corrosion resistance.
Next, we move into materials that sort of bridge the gap between perfectly ordered crystals and completely random glass. The Metasilicates.
Right. These are highly ordered, but only on the nanoscale. The key example here is MCM41, synthesized in 1992. This material features a highly ordered hexagonal pore structure. It's a perfect nanoscale honeycomb.
How does that look visually?
Imagine taking a bundle of perfectly uniform microscopic spaghetti strands and turning them into glass. The structure consists of cylindrical silica rods, all arranged in a 2D hexagonal lattice. The pores are incredibly precise and uniform.
How do you synthesize such precise order at the nanoscale?
You use a method called surfactant-directed synthesis. You use a surfactant, a soap-like molecule, in a water solution with the silica precursor.
And the surfactant molecules self-assemble.
They self-assemble into these rigid cylindrical clusters called micelles. The silica then condenses around these micelles, coating them entirely. Once you burn or wash away the organic surfactant, you're left with the uniform hexagonal pore structure of the silicate framework.
It's a triumph of chemistry controlling nanoscale self-assembly.
It really is.
Finally, let's cover the advanced chemistry technique of sol-gel synthesis, which allows us to produce materials like sols, gels, zero-gels, and aerogels with extremely high control over the microstructure.
Sol-gel chemistry is fundamentally a wet chemical method. It lets researchers move from a liquid precursor solution to a solid, amorphous material at relatively low temperatures. The precursors are typically metal alkoxides, which are organometallic compounds.
And the process relies on 2 primary chemical steps that happen sequentially in the solution. The first is hydrolysis.
In the hydrolysis step, the silicon alkoxide reacts with water. This reaction essentially removes the organic group and replaces it with a hydroxyl, an OH group, forming what's called a silanol. So the silicon atom now has a reactive hydroxyl group attached to it.
And the second step, condensation, links the atoms together.
Condensation follows immediately. 2 of those silanol groups react together. They remove a molecule of water and form a siloxane bridge, a silicon-oxygen-silicon bridge. That's the linking step.
Repeated reactions build the network.
Repeated hydrolysis and condensation reactions lead to extensive polymerization and the formation of a 3D network that eventually precipitates out of the solution as a solid gel.
And this precise, controlled process allows for the production of incredibly unique materials.
It allows for fine control over porosity and density. For example, by carefully drying the gel, you can produce highly porous, low-density materials like aerogels, which are famous for being excellent thermal insulators. Or you can produce fine, monodisperse powders for high-quality, dense ceramics. It's a method that marries chemistry and structural engineering.
This has been a truly comprehensive exploration of the silicates and aluminates, the materials that really structure our world. Let's quickly summarize the structural path we followed.
We started with that isolated building block, the silicon-oxygen tetrahedron, and we defined the entire structural taxonomy based on just how many oxygen vertices were shared.
Right. We journeyed through the isolated zero-dimensional orthosilicates like olivine and garnet, which promote high density and hardness.
Then we connected the units to form one-dimensional structures. The paired pyrosilicates, the infinite single chains of metasilicates, and the complex amphibole double chains.
Then we stepped into the two-dimensional world of the phyllosilicates, like mica and kaolinite, where the concept of weak interlayer bonding, whether it's a large potassium cation or just delicate hydrogen bonds, directly results in the material's easy cleavage and softness.
And we culminated with the three-dimensional tectosilicates. That included the perfectly balanced quartz, the isolated cages of sodalite, and the channel-rich zeolites, which are indispensable for charge balancing and ion exchange applications. We finished with the random networks of glass and the engineered precision of nanoscale materials.
And the crucial point throughout all of this is that structure is destiny. The ability of zeolites to filter contaminants, or the ease with which mica can be peeled into thin sheets, they're not accidents.
Not at all. They're direct, predictable consequences of the way those oxygen atoms are shared. And as we close, it's worth reflecting on the human effort required to map this microscopic world. We rely on the structural classifications charted by these intensely focused minds like Lima de Furia and the theoretical underpinnings laid by figures like Cardano and Pauling. Every crystal structure we described is the culmination of generations of meticulous observation and reasoning.
So the next time you look at a piece of glass, a concrete sidewalk, or even a piece of granite, remember that you are looking at a complex, interlocking atomic map. A map defined entirely by the sharing and linking of those tiny silicon-oxygen tetrahedra.
Thank you for joining us on this deep dive into the bedrock of the Earth.
We'll catch you next time for more material exploration.